So today we're going to continue just right where we left off yesterday, and that will be this true or false exercise. So please read these and decide in like the next 3 minutes, maybe just 1 or 2, or as many as you can, whether these statements are true or false. There might be a bit of noise today in this lecture because there's a construction site outside my apartment. So maybe, I don't know if you can tell, if you can hear that. And if you have questions about these true or false questions, then just ask me. Okay, any ideas or thoughts about these true or false statements? Can you pick one and tell me whether it's true or false? Any vague ideas? Oh, Jency wrote in the chat. Let me check. Actually, participant list is. Oh yes, I can zoom in a little bit. Didn't see that. Yes, two is definitely false. Can you you want to that in the chat? Can you explain why? So a transformation that we look at for eigenvalues has to be from a vector space to itself. So we can't go from the zero vector space to V, because then, so if you look at this equation, T of V is equal to lambda times V, and if T was going from V to W, then this means that this is a vector in V and this is now a vector in W. But we can't, it's not possible to just have a vector from V and W all of a sudden just by multiplication. So we have to assume for eigenvalues that they're the same. But what Yardan said was correct. So if you have a rotation, then if we say we have R2 and we have the rotation by a certain angle, so we rotate our theta is a rotation by not 0 degrees, by some positive degree, and it has no eigenvalues. Okay, any other? Right, and not 180 degrees. So, and not 180 degrees. Okay, so one is true because kernel is 0-dimensional. Yes, exactly. So one is actually true. And the way we can see that, I'm running out of space, but I'm gonna just answer this right here, and then maybe I'll create a new page. So one is true, and the reason we can see that is from a previous proposition. What was it? It said that lambda is an eigenvalue if and only if the determinant of this expression is 0. Now, what happens if we set lambda to 0? Then we have just the determinant of t is 0. So this means that that 0 is not an eigenvalue, is equivalent with the determinant of t minus lambda I is not 0, but if this is 0, then it just vanishes. So this is just the determinant of t that it's not 0. And we've had last week that this is then equivalent with being invertible. Yes, this is true. And Adrian already said that in the chat, it's true by the definition. So if let me explain this here. So if determinant t minus lambda in is non-zero, this means that it is an eigenvalue. That was the proposition I just showed you. Then this means that that t minus lambda, oh, sorry, I should have written IDV is not invertible. And this means that t minus lambda IDV has non-trivial kernel, and every non-trivial vector in there will be an eigenvector. So as soon as you have an eigenvalue, it has to have at least one eigenvector. What about the rest? Did I miss anything in the chat? Yes, that's also true. So if V is an eigenvector, then also 2V. So let me just say that if you have 2 times V is lambda 2V, and so on for any scalar. Oh, we're just missing one. So the last one, what about that? Right. That's correct. Okay, so apparently I only came up with the one wrong statement. The others seem to be true. I'm not going to say anything about the last because we're gonna just see we're gonna see this in the future again, and there's also no space. But I think it's clear that if you compute the characteristic polynomial lambda can only appear n times in an n matrix because you put in n lambdas along the diagonal of the identity matrix. Okay, so let's do this discussion right away. Yeah, I'll give you 3 or 4 minutes to think about this, and then we'll look at this. So this is basically just a last check to summarize everything that we've done so far. Benjamin asked in the chat, what if 0 is an eigenvalue regarding the third statement? That's still fine if, I mean, if you combine this with the first statement, then it just says that T itself is not invertible. So it has a kernel. So there are things in the kernel, and then everything in the kernel of T itself will be an eigenvector to the eigenvalue 0. Yeah, so Sam just replied with the same answer that I just gave. Okay, so this is actually designed to not take long. This as you'll see, it's a exercise designed to be quick. Can someone tell me what how to compute the characteristic polynomial for this matrix? So we can call this C. I think I want to call this A. It doesn't matter. By convention or by definition, they're the same. Can someone just tell me, just unmute yourself and tell me? Yes, Adrian.
Yeah, I think basically you just want to deduct lambda from all of the diagonals of A and then just calculate the determinant of that.
Yes, correct. So I'm going to write this down. Okay, and then?
Yeah, and then if you expand like along the first row, it's pretty easy because the last one is 0 anyways. And then you'll just get 2 minus lambda squared times 1 minus lambda.
Yeah, do you mind expanding along the last column?
Oh, the last column. Yeah, that looks even easier, I guess.
Yeah. I mean, it's totally correct what you did, but let's just for time's sake, just like do this. So what does this mean?
Yeah, so you just check out like the signs, and then for this one it should be I think a negative then. Also
No, it's a plus. It's -1 to the 3 plus 3.
Yeah. So you just have that one 1 minus lambda, and then you just erase like the column and row, and then you get just 2 minus lambda squared.
Yes, exactly. So so then this is the cofactor, and this is the sign. So we get the determinant of 2 minus lambda, 1, 0, 2 minus lambda. And then we see, well, the determinant of the 2 by 2 matrix is A D minus BC. So this is plus 1 minus lambda, 2 minus lambda squared. And this is what I mean by quick, because now we can just read off the eigenvalues. Can someone tell me? Yes, exactly. So the eigenvalues are lambda 1 is 1, lambda 2 is 2, and the multiplicities should be more specific with oh, we didn't. Oh, never mind. We didn't cover this. Yeah, this is next next slide. Okay, so what about the eigenvectors or the eigenspaces? First, let's compute E lambda 1 of A. This is what? So we're just going to compute the null space of this matrix, where we explicitly put in lambda 1 for lambda, and lambda 1 is 1. So we have the null space of 2 minus 1, which is 1, 1, 0, 0, 2 minus 1, which is 1, 0, 2, 3, 1 minus lambda is 0. Well, if we do a quick row reduction, so we can use this value. That's the only non-zero entry in the second row, and we can cancel this one. We can subtract 3 times from the last row, and then we get this equal to the null space of 1, 0, 0, 0, 1, 0, 2, 0, 0. Or I should not look at the chat when I'm in the middle of something. But yes, that's correct. And then we just use this number to kill this one. So we have the row reduction is done. And well, now we see that this is just the span of 0, 0, 1, because the basic solution, or the only basic solution, is 0, 0, 1. Does that make sense? And likewise for E lambda 2, we compute the null space, and then we plug in 2 for lambda. So this gives me 0, 0, and -1 on the diagonal. And the rest remains the same. So it's zeros except for the 2 and the 3 in the bottom row. Is that really correct? No, there's a 1. Sorry, there's a 1. Is that correct? Yeah, it looks correct. Okay, so this is my my matrix, and then we can use this one to cancel this, and then we compute after row reduction the null space of Well, I'm also going to resort. I'm going to reshuffle the rows so that I have the nice steps in the row reduction, the reduced echelon form. And then lastly, I will also divide by 2. And so from this, we can read off that basic solutions well, actually, there's only one basic solution, because we see that we have 2 leading ones, and we have one free variable. So there's only one thing that is free. So we have just one parameter and just one basic solution. So the basic solution is 1, 0, and 2. And this means that E lambda 2 is equal to the span of 1, 0, 2. And these basic solutions are also bases. So Yardan just asked about whether we should go back from the tuple, the coordinate vectors, to real vectors. And the answer is, well, you can, it doesn't matter. It's the isomorphics. So either way, there's no data lost or gained in either way. The thing is, though, I didn't tell you what the basis alpha is, so you don't even know. So gamma alpha inverse is not known. You cannot go back into the vectors this time. If it was given and your question was to give the polynomials in this, if these are like polynomials, then yes, you would have to go back. Okay, any questions? So this basically is all that we're going to cover about eigenvectors and eigenvalues just for this section. The book might have more examples if you're interested. But the idea is, I mean, the discussion pretty much, the true or false, we're supposed to give you some ideas that what's possible, like, is there always eigenvector and how they behave in general. And you see that we've talked about that there's not always an eigenvalue, for example, for the rotation. And if there are no questions, as it seems, then I want to move on to diagonalizability. It's a terrible word to pronounce, especially quickly, but I'll give my best. This is now section 4.2, and it's a natural thing to ask after eigenvalues and eigenvectors. So the definition of what it actually means to be diagonalizable is straightforward. It means that if you have a linear transformation where we have enough eigenvectors of this transformation so that we can create a basis of the vector space in terms of eigenvectors. So we only allowed to use eigenvectors, and we're supposed to find a basis. The thing is, though, a basis is a very special family of vectors. It has to be linear independent and it has to span the space. And maybe, so in the past example, for example, here, this we just looked at, we only had two eigenvectors, 2 basic solutions, but the space is 3-dimensional. So in this case, this would actually pose a problem, but let's look at that later and first go through this definition. And the question, why does this definition make sense? Why is this called diagonalizable? Well, if we look at the matrix representing T for a basis consisting of eigenvectors, then we'll observe something. So remember the algorithm that I showed you. It says, well, apply T to the vector alpha 1, and then you evaluate the result in the alpha basis. That's going to be the first column of the matrix representing T in the alpha basis. Now, by assumption, this is an eigenvector. So it's some lambda, let's call it lambda 1 times alpha 1. And if we evaluate this in the alpha basis, then what this is going to be. This will be the vector containing lambda and then zeros, lambda 1. Likewise, if we do this for the next one, so if we have lambda 2 and we evaluate t on this, alpha 2 is also an eigenvector, or every alpha in this basis is an eigenvector, then this will be multiple of lambda 2. It might be lambda, the same lambda, it doesn't matter, just some number times alpha 2. And in the alpha basis, alpha 2 itself is just a vector. Well, every coefficient in this linear combination is 0. Only the coefficient of the alpha 2 is non-zero, which is lambda 2. So we get the coordinate tuple, which is 0, lambda 2, and then zeros. So we can play this game until we get to alpha n. And then we see that from this, that the transformation in the right basis looks like alpha 1, alpha 2, all the way to alpha n, and everything else is 0. And this is what we call, this is a diagonal matrix, because it only has non-zero values on the diagonal of the matrix. And there's many reasons why this is nice. Well, let's compute the determinant of t alpha alpha. This is just going to be the product of all eigenvalues. So this is lambda 1 times lambda 2 times lambda n, because you can always just expand along one of the rows or the columns, and then everything is 0 except one cofactor. Another reason why this is nice is because if you have a diagonal matrix and you multiply this with itself, so like say you square this, then this will be the matrix lambda 1 squared, lambda 2 squared, lambda n squared. So if you multiply a diagonal matrix with itself, you just multiply the diagonal elements. So there's a lot of reasons why you are looking for, why you want to talk about, why you would desire diagonal matrices over normal matrices. And I've told you now this definition that if they are available, then we call this transformation diagonalizable. Okay, so now the goal for this section and this remaining hour and maybe a bit of the next one is going to be to find a condition and to determine whether a transformation is diagonalizable or not. And then also, how do we get there? Like, what is the diagonal form of the transformation? Okay, so for this, I'm going to define two things. First of all, the algebraic multiplicity. And we've just seen that in this previous example, we've seen that CT of lambda with lambda minus 2 squared times lambda minus 1. Let's actually put this to the 3, why not? And then this is the multiplicity, the algebraic multiplicity is the degree of with which the characteristic polynomial vanishes. So if you write this in these linear factors, so this means this is the linear factor of 2. So we know that one eigenvalue is 2. And then we look at its exponent and we say that the multiplicity of lambda 2 is equal to 2 because of that exponent. If we look at this factor, well, it tells us that if we plug in 1 for lambda, it will also vanish. So this means another eigenvalue is 1. And the multiplicity, the degree of this root of this polynomial is equal to 3 because, oh, sorry, this is supposed to be 1. We could just say multiplicity of 2. The multiplicity of 1 is equal to 3 because we have the third power of this linear factor. And the way that you can look at this graphically is, well, if you have the second degree 0 of polynomial, it looks like this. If you have a third degree polynomial, it looks like this. Well, something like this. Nope, still not. Yeah, more like this. So this is x to the 3, and this is x to the 2. So I guess you get the idea. And then the second definition is the geometric multiplicity of an eigenvalue. Remember that we were associating an eigenspace to every eigenvalue. And well, it's a subspace as we've shown, and subspaces have dimensions. That's just a fact. Like every subspace has some dimension. And so we just call the geometric multiplicity the dimension of E lambda t. So in this example, let me actually now go up again and see here that this means the dimension of E lambda 2 is equal to 1, because we have one basis element in this eigenspace. And if we compare, if we compute, yeah, that's what I wanted to write here. If you look at this 2 and this 1, there's nothing. Then we can say that the multiplicity of this previous example of lambda 2 was 2, and the multiplicity of the first eigenvalue was 1. And this also tells you immediately that if you compare this multiplicity of the eigenvalue lambda 2, which is 2, and the geometric multiplicity of lambda 2, the dimension of E lambda 2 is 1, so they don't always agree. Well, Yuan just asked like what to do if the polynomial doesn't factor easily in linear factors. Well, I guess you have to try harder. I don't know. I guess like if you factor it in linear factors, then it's literally just the appearance of this linear factor. Oh, if it's not factorable, like if you have, for example, x squared plus 1, this is not equal to x minus lambda, x minus lambda 1, lambda 2 for lambda 1, lambda 2 in the real numbers, then this means there's simply just no eigenvalues. But if there are no eigenvalues, then we can't talk about multiplicity of these eigenvalues. And we're going to talk about that when we're done with this section, and we talk about complex numbers. That's actually the reason why we want to introduce complex numbers. Okay, so now proposition. And this is going to be very useful. We have like now one proposition and one corollary leading up to the important theorem to answer our question whether or not a transformation is diagonalizable. Well, it says that if we have eigenvectors v1 to vk, and we have distinct eigenvalues, so this means that these are eigenvectors with different eigenvalues each, then the family of all of them is linearly independent in V. So this proof is done by induction. And the base case is when k is equal to 1. So this means that V1 is linearly independent because Vi or V1 can't be 0. That was an assumption, otherwise it's not an eigenvector, and a family with one non-zero vector is always independent. So then we assume we assume that it's true for some k equals to m. And we consider v1 to vm plus 1, the next step. And now what we want to show is that, well, we want to test whether or not there's a linear combination a1 v1 a m plus 1 v m plus 1 that is 0 with non-trivial coefficients a1 to am plus 1. Well, what we do with this is we just apply t. And then we see that t of 0 has to be equal to t of a1 v1 all the way of this linear combination. But what happens when we apply t to linear combination? Well, t is linear, so this means we can write this as a1 times t of v1, and we just pull out all the coefficients, and also we separate the sum into a sum of t of vi's. On the left-hand side, we also see that because t is linear, this has to be 0. Okay, now we invoke the fact that these are all eigenvectors. So there's some lambdas such that t of vi is lambda I times vi. So we're just going to replace each of them. Now comes the ingredient that is probably hard to guess. That's the non-trivial step in this proof. So we let me give this equation a star, and like let's put a box around this. So we just multiply with lambda m plus 1. So then we see that this equation star that I put a box around becomes 0 is equal to a1 lambda m plus 1 v1, and so on. So every summand just gets a lambda m plus 1 for no good reason. Well, actually, the reason is that I have something in mind that I want to do. And now you can observe that the last summand of this combination is equal to the summand of this combination, the last summand. All the other sums are different because all the other summands here have different lambdas, and all the summands here have the same lambda m plus 1. Should have written this clearly. So this is a lambda m plus 1. So they have all the same lambda, but these ones have different lambdas. So if I subtract now subtract from another name. Okay, let me give this also a name, and let me call this double star, just to refer to this easily. From double star, then you see that all the last summand cancels, but the other ones don't cancel. And then we get that 0 is equal to a1 lambda 1 minus lambda m plus 1 v1. And this goes up all the way to am lambda m minus lambda m plus 1 vm. Okay, so now what I've done is I've reduced the linear combination of m plus 1 vectors down to a linear combination of m vectors, the first m vectors. And as I said that by assumption, v1 to vm are independent. I also said that the lambda 1 or the lambda I minus lambda m plus 1 is non-zero because all lambda I are distinct. So no two lambdas are the same. So all of these have to be non-zero. And this implies that A1 to AM have to be 0. Otherwise, I would have a non-trivial linear combination of independent vectors equal to 0, which can't be true. So this means that that now I look at star again, but it's the same coefficient. So this means literally it says 0 is equal to 0 v1 plus 0 v2, 0 vm plus am plus 1 vm plus 1. And this finally also concludes that am plus 1 is equal to 0. Because now everything else here, this is all 0. And we only have one summand left. But vm plus 1 is non-zero because it's an eigenvector. And this implies that we get that v1 to vm plus 1 is also independent. And this is the end of the proof because now we've completed the induction step. And the induction tells us that this is now true for any k. Any questions about this? So this is really nice actually, because so before, if you go back to the example again that we ended with in the last section, and you take these two eigenvectors. Say you take this is in the eigenspace E lambda 1, so it's an eigenvector with respect to the first to lambda 1, and this is an eigenvector with respect to lambda 2. Then we didn't even check that these are independent. Well, they obviously are, but we could have said, well, they have different eigenvalues, so they have to be independent just by this proposition. Did I guess this a name? No. But I can just comment. So as an example, or if we applied to the discussion above, this would imply that 0, 0, 1, which is in E lambda 1, and was it 1, 0, 2, I believe, in E lambda 2, and this actually checks out. This is indeed true. Now you might wonder, why do we need to prove such a powerful theorem just to check these two vectors that we could have done more easily? Well, we're not always going to be able to look at compute the eigenvectors directly. We maybe just want to use arbitrary eigenvectors of different different eigenvalues and then conclude that they from a basis, because remember the goal was to compute like to find a basis of eigenvectors, and independence of this basis is going to be like of this set is going to be very important to conclude that it's a basis. Okay, so before we see what's ahead, so before we take a break, let's have a short discussion and then let's look at the corollary after that. So what is the intersection of eigenspaces to distinct eigenvalues? So let's I'll give you like 2 minutes or so. Just think about if we have E lambda of t intersect E sigma of t, lambda and sigma eigenvalues of t going from v to v, but lambda and sigma are not the same. Then what is the intersection? Oh, because say if lambda is equal to sigma, well, then it's clear that E lambda is equal to E sigma, and therefore the therefore E lambda intersect E lambda is just E lambda. So if lambda and sigma are the same, then there's nothing to be computed. Does that make sense? Okay. I mean that's a good question. I could have also phrased this this discussion differently. What is the intersection? And then we could have made cases either they're the same or they're different, and then we would have gotten the same answer. But I wanted to particularly focus on the second case where they are different. Does anyone have an idea how to start? So what would it mean for V to be inside the intersection? Just in plain words in English, what does it mean for a vector to be in two eigenspaces, two different eigenspaces? Oh, the L is the lambda. Okay, no, I understand. Yes, that is correct. So Yuan said that that we can say that, well, if we apply t to v, then this is lambda times v by being in the first eigenspace, and t of v is also sigma times v because it's in the second eigenspace. This means this implies that and this implies that. But now what happens if we subtract lambda v minus sigma v? Well, on the one hand, let me write this over here. So lambda v minus sigma v is equal to lambda minus sigma v. But we can also write this as t of v minus t of v, which is 0. Now, sigma minus lambda, this is non-zero because lambda is not equal to sigma. So this means that this implies V has to be 0. Well, I shouldn't have said that this is an eigenvalue. This is not an eigenvector to both. It's in the eigenspace. So this includes the case that it can be 0. That's the right phrasing. But the result now is that two eigenspaces with distinct eigenvalues can only intersect trivially. Yeah, exactly. So the eigenspace contains the eigenvectors and the 0. Yeah, the chat noticed that, and you guys they said that yourselves. Okay, this is also very interesting to know, and it's going to be helpful for a final theorem in this section. So we're going to work towards that. Now let's quickly look at this corollary. This is a corollary of the previous proposition. And this is quite quick to prove, but it's quite cumbersome to read and understand, I guess. Like the notation is kind of this is absurd. So we can simplify this by just saying, well, we have different. In the case that we just have two different. Let me say k equals 2 example, just to give you an idea of what this notation means. So we're going to have k distinct this is not eigenvectors, this is eigenvalues. Yes, so we have distinct eigenvalues. That's what I wanted to say. And for each eigenvalue, consider a family of independent eigenvectors. So this means for k equals 2, this would mean we have lambda and sigma. We have e lambda and we have e sigma. And then we consider v1, v2, v3, say in here. So these elements, these eigenvectors for lambda. And then we have w1 and w2 in e sigma. So these are eigenvectors for e sigma. But because I want to make this statement general, I have to say that there are k of them, and there's any number n sub j is the number of eigenvectors I consider for the eigenvalue lambda j. So this is just notation saying that I can have as many eigenvectors as eigenvalues as I want. That's the k. And for each lambda j, I consider any number. So this is 3, this is 2, but it could be anything. And this number, so in this case, n1 is equal to 3, n2 is equal to 2, and nj could be equal to anything if I want to have more or less eigenvectors for this particular eigenspace. Okay, but then the goal, the upshot of the statement of this corollary is that if I take the union of all of these, so if you take the union, and in this example, it will be v1, v2, v3, w1, w2, and I just throw them all in the same family, then this is still independent if the families to begin with were independent. So if these are independent, then this is also independent. And the notation now just says, well, I take the union. And these are all the vectors coming from e lambda 1. And these are all the vectors coming from e lambda k, and there could be some in between. We're going to use this corollary and then a theorem later, and then it makes sense why we need this notation. Any questions about the notation only, or can we just prove this? Okay, so the proof is not very hard. It's corollary, so it should not be a proposition itself. But what we're going to do is we consider linear combination. Now it gets tricky. A11 V1. We consider a linear combination of all of the vectors in S. So test S for linear independence. So this means we have to have the V1 1. Actually, this is supposed to be a 1. And then the J is somewhere in the middle. V11 with some coefficient, let's call it A11 plus A21, V21, AN11, VN1, and so on. And then we have the AK1, VK1, ANK, VNK, KK. Okay, so in the example, we would just have a linear combination of the V's and the W's in the set S. So if this is equal to 0, then observe that this linear combination itself, this is some say W in E lambda 1. And so every chunk in this expression is some vector, some eigenvector in some eigenspace. So this may be some U in E lambda K, and so on. But then in total, the sum, this is 1 times this W plus other vectors. Let's call this W1, WK. W1 plus 1 times W2, and so on, plus 1 times WK. We just give these linear combinations in each eigenspace a name. So this is going to be a linear combination of vectors of different eigenvalues, but this is not a non-trivial combination because the coefficients are 1. So this violates this contradicts the previous proposition. Because, well, yeah, let me just stop there, because this is a non-trivial combination unless all the W's is 0. But then what we're left with is just the what we then left with is just the this means for all J, AJ1, VJ1 plus ANJ, J, VJ, NJ is equal to 0. But V1 to VNJ assumed to be linearly independent. So each of these families, in this case, the V's and the W's here, were assumed to be independent to begin with. So this means that if we consider only these separately, then this means that the coefficients have to be 0. But then we're done because now we've shown that all the coefficients in this have to be 0 as well. Okay, let's take a 5-minute break and come back at 2:15. And then we'll wrap up this section with the final proof and an example. Any questions right now before we take the break? Oh, how did we get one? That's a good question. So if we have this combination to begin with, and we just define the W's to be the first bit, then we can consider we just consider a 1 in front of all of this. So that means that for the right definition of W, there will be a 1 in front of the coefficient. That's just that's just interpretation I give this. So I interpret this partial sum, these summons up until of all the vectors in the first eigenspace as a new eigenvector. Well, linear combination is just a new vector. And then this just appears on its own. And so if there's a coefficient, the coefficient is 1 naturally. So it wasn't random. It was by design of W, this is the coefficient appearing in the sum. And I think there was another question. Eigenspaces are always subspaces, because we put the 0 in naturally. Okay, I'll be back at 2:15 unless there are other questions. Yes, Aditya, that's now the follow-up question to what I just said. So the W1 to WK, they have to be independent because of the proposition before. So this is exactly where the proposition, what was it, 424 comes in here, because now the W's by construction, they're just eigenvectors, each of them in a different eigenspace, and they have distinct eigenvalues. So any family of eigenvectors of 2 different eigenvalues has to be independent. Okay, how do I stop pause the recording now? The recording. Thanks for reminding me. So we're back recorded. It says that the geometric multiplicity is always less or equal than the algebraic multiplicity. And it also says it's as a lower bound by 1. Well, this part, this is clear. This is actually clear from previous discussion. The discussion said that every eigenvalue has at least 1 eigenvector. So it has to have at least dimension 1. But the other one is non-trivial. This is, well, you have to go through the proof. But it's interesting to see that the algebraic multiplicity is bounding the geometric multiplicity. So now let's get to the final theorem of this the subsection. Well, this is the answer to our question at the beginning. So a transformation is diagonalizable. That's the key part. If and only if 2 things happen. First of all, if the algebraic multiplicities of all the eigenvectors sums up to the dimension of V, and we have that for each eigenvalue, its algebraic multiplicity and geometric multiplicity agree. That's very important. Well, you can see that the first one exactly takes care of if the roots are not necessarily real valued, then we might have a problem. And if you go through the proof, you're gonna understand why this is important. So the proof is very constructive, and this proof honestly is easier than the proofs before, because the proofs before were technical, and this one is just more high level. We're just gonna use the results from before. So the goal is, well, I want to do this direction first. This is the constructive direction. So assume we need to show, need to construct a basis of V of eigenvectors. I mean, by definition, that's what it means to be diagonalizable. There's a basis of eigenvectors, so we're just going to construct one, and then this shows it's diagonalizable. So we can start with compute each E lambda I, so all the eigenspaces, and pick a basis beta I for each of them. Next, we consider beta, which is just the union of these bases. So beta 1 union beta 2 and so on union beta k. And we want to prove that this is the basis we're looking for. This is the basis of eigenvectors. Well, the first one, the first thing we need to show for this so the first subpoint of this is, well, each beta I is independent because it's a basis. But this implies by the corollary 425. Was it 425 or was it? Yeah, it was this corollary that if you have the union of independent families, then it's still independent if they come from different eigenspaces. Beta is also independent. The next part is we need to show, well, it has to have the right number of elements. It has to span the whole space. So beta I has m lambda I elements. This is the algebraic multiplicity and also the geometric multiplicity by our assumption. And so because so this means that beta has m lambda 1 and so on plus m lambda k which is equal to dimension of V elements. And there was a proposition before that said if you have a family of independent vectors with the same number of elements as the dimension of the space, then it is a basis. So that's what I'm invoking here. So these two things are enough to say that beta is a basis. Is a basis of V. Well, the nice thing is the way that we constructed this basis is we only use eigenvectors. We didn't use anything else. And beta consists only of eigenvectors. Yeah, I believe that's the end of this one direction. So it's very, very constructive. We just use the corollary, and we say that we just combine all the bases that we can choose for the eigenspaces. So the first one, so I did this direction where I assumed these two, and then I showed this. So technically we now have to do the second one. I don't want to go into too much detail. So we're just going to sketch of the proof of this one, of this direction. So any questions of the other about the other part so far? So I'm not sure if this is actually only sketch or this is thorough. Well, I mean, you can tell me if you think things are missing. So assume that no, so the way that this so I'm saying that these two have to be satisfied. This is equivalent with T diagonalizable. So if I do, okay, now it's the other way around, but if I do this direction here, then I assume 1 and 2. So I assume them as given. And now if I do the other way, so if I assume it's diagonalizable, assume T is diagonalizable. And show 1 and 2. So T diagonalizable means that there's some basis alpha of eigenvectors. Well, let me compute T, the matrix of T in this. As I explained before, this is just going to be a diagonal matrix with lambda 1 to lambda n. And lambda I is not necessarily distinct. Because I have to have n of these, and they might repeat. So I'm not going to say that they are distinct. Well, and now if you compute the Quadratus polynomial of this, then this is equal to the Quadratus polynomial of any matrix representing T. In particular, I can choose the eigenbasis. I guess that's not the eigenword. And so this is the determinant of lambda 1 minus lambda, lambda 2 minus lambda, and so on, lambda n minus lambda. So you can see diagonal matrices are really nice. I mean, I mentioned that. So the quadratic polynomial is just lambda 1 minus lambda times lambda 2 minus lambda, lambda n minus lambda. So it already comes up in all these in all these linear factors. So this proves this proves 1. Because you could combine these factors if the lambda 1 is equal to some other lambda. For the second one, we need some more work, and I'm just going to leave this as an exercise because I want to move on with other content. But this is not the hard direction. The hard direction was to use all the corollaries for this. This is the non-trivial direction. And just as a remark, maybe I can also say well, I have a separate page for remarks. Yeah, so for one remark, if T is diagonalizable, then we can write V as the direct sum of the eigenspaces. And then the basis, of course, this is basically what we used. This statement is equivalent with saying that we can create a basis by combining all the bases of the eigenspaces. But I didn't use this this before, so I just wanted to add this as a remark. Okay, so now that this is proven, let's do one example, and then let's discuss in the same vein. I mean, let's do that afterwards. So let's do this example first. So diagonalize this if possible. Oh, actually, there's not a discussion. I think I'm just gonna like explain, and then we're just gonna see the result. So first of all, I'm gonna compute the correctness polynomial, and this is the determinant of 2 minus lambda, 1 minus lambda, 2 minus lambda, 1, 2, 0s here. And I'm going to again expand along the last column. So this is 2 minus lambda times the determinant of 2 minus lambda, 2, 1 minus lambda, and 0. And this is equal to 2 minus lambda squared, 1 minus lambda. So I have eigenvalues. Lambda 1 is equal to 1, lambda 2 is equal to 2. And the multiplicity of 1 is 1, and the multiplicity of 2 is 2. So to decide whether it is diagonalizable, I need to check these two conditions in the theorem. So by the proposition, I know that the dimension of the first eigenspace, E lambda 1, is less or equal than 1, which is the first multiplicity. But I also know that it's lower bound by 1. So this means that the dimension of the eigenspace is exactly 1. For the second eigenspace, I need to do some work. So I actually need to check. I need to check what E lambda 2 is. This is the null space of 0, minus 1, 0, 2, 0, 0, 1, 0, 0. And I guess the row reduction this time is very simple. You just choose this one and you cancel these two. So now we just create the null space of a matrix that looks very simple. So the null space, you can just read off two basic solutions. One of them is this vector, and the other one is just this vector. So indeed, we can see that the dimension of E lambda 2 is 2. And now we can decide whether it is diagonalizable or not. Can one of you maybe tell me what can we conclude about, like, from this about diagonalizability of T? Yes, exactly. So you want to observe that both conditions of 4.2.7 are met. The first one is that m lambda 1 plus m lambda 2 is equal to 1 plus 2, which is 3, which is the dimension of V, or in this case of 3. And the second condition is that m1 or m lambda 1 is equal to the dimension of e lambda 1, which is 1, and m lambda 2 is equal to the dimension of e lambda 2, which is 2. This means it is diagonalizable. And I don't know if I mentioned this explicitly in a proposition. So now in this right, let's look back at the example. So compare which page was that? So we had a discussion before, right? So this discussion just said, well, let's find the eigenspace of this matrix, and this is, I guess, page 7 in the PDF. So here we see that this is not equal. So I should color code this some way. This is not equal. I'm like just an aside. This is not equal to m lambda 2, which is 2. And this means that this one would not be diagonalizable, just to give you a counterexample. So if you look back on this example and you already had, you already looked at theorem 4.2.7, we can say that this is an example where it's not diagonalizable. And the reason is, I mean, the reason now is very, very nice to see that we have two eigenspaces, but they only have bases of size 1 each. So if you combine the bases of these two eigenspaces, which is this vector and this vector, we get a linear independent family of size 2 in R3, but this is too small to be a basis. So the theorem basically fails if you're not able to build this basis out of bases of eigenspaces. That's the idea behind this. And so then if you compare this with the remark that I made at the end, then these eigenspaces are too small that the direct sum exists, but it's not equal to V. So I could say otherwise, this is contained but not equal. So this is too small. Okay, and this is this discussion. Let me just skip this for now, but let me just hint at why this condition is important. So the lecture of Sean Upal actually, the section of Sean Upal actually phrased this slightly differently, but still it means the same. If you look at the corresponding polynomial of this matrix, we will see that this is lambda times lambda squared plus 1. So this does have an eigenvalue. This does have eigenvalue 0, and the dimension and m0 is the dimension of e lambda 0 of e0, which is 1. But but the dimension of R3 is strictly greater than M0, which is 1. So this means we could equally say that it has to have, like, the real eigenvalues have to be all present or something like that. That's another way of phrasing it. But just to give you an idea why this condition, this first condition, is important. All right, I want to make one more remark because I guess this is important, and this is something I didn't mention so far. So it connects the change of basis section with this section. So finding if T is diagonalizable, we have a basis beta such that in this basis, the matrix representing T looks like a diagonal matrix. So for any other basis, alpha, we can find a change of basis matrix P such that T beta beta, usually it's phrased the other way around, that T alpha alpha is equal to P inverse T beta beta. So this means that if T is diagonal, and this is probably a proposition in the book. Let me just check that I can just refer to this. Yeah, this is basically sketching the proof of a proposition in the book. It's giving you the idea. It means that T is diagonalizable if and only if T alpha alpha is similar to a diagonal matrix. For any basis alpha. And this is essentially the proposition 422. So it just means that if you look at this idea of finding a new basis in which it is diagonal, and you remember that we had this thing called change of basis, then it's clear that if you have two bases, there is just a way to go between them. And the way that the matrix of T changes is exactly by change of basics operation, which just means that the original matrix and the new matrix will be similar. Okay, so I think I now have told you everything I need to tell you about this topic. Are there any questions before we go to complex numbers? Wait, why is there another remark page? Doesn't look like there are other questions. Okay, so then do I have, oh, I don't even have. Okay, so this is the second set of slides for this week. And I was hoping that we would have a few minutes to talk about this. So the motivation is basically the question that Yuan asked today. What happens if the quadratic polynomial doesn't have any roots? So as a bad mathematician, you would just say, well, we can't do anything and go home. But as a good mathematician, we should always ask, how do we make this happen no matter what? That's the attitude that you need to have. So in order to make this happen, well, we need to invent something and realize this problem and like turn this problem into an opportunity. Yes, rotation. So this is the rotation, by the way, by 90 degrees. And I said this has no real roots. There's no real eigenvalues because so far every vector space was a real vector space. And if there are no real eigenvalues and there are no, so I'm talking about real things so far. Andrew is jumping ahead and talking about complex eigenvalues. So that's the motivation. That so CA of lambda is equal to 0 if lambda is equal to plus minus the square root of -1. So the question is, what is this for this characteristic polynomial? All right, so wait, why is this only, oh no, 1 second, did I not push this? Okay, now we, 1 second, I have to go back, delete this, then go over and open this in GoodNotes. Yeah, when version control fails you. Okay, now we have the up-to-date slides. Okay, so as I just said, the square root of -1 will solve the problem of finding roots of this characteristic polynomial. So now I'm going to define the set of complex numbers to just be the vector space R2, meaning tuples of real numbers, A and B are going to be real, with an additional multiplication, which I define in this manner. And because this is the tuple perspective on the vector space R2, I can also say, well, let's pick a basis 1 and I. And then if I apply this gamma inverse map, then gamma inverse with respect to this basis will just create the linear combination with A and B as coefficients of in front of the basis elements, but the basis elements are 1 and I, so we just write this as A plus IB. Okay, so let's just look at this discussion and I'll give you a few minutes to think about this. First of all, for these two tuples, which are now considered to be complex numbers, first of all, write them in the basis 1 and I, and then compute the product. And then consider the span of just the first basis element 1 and show that it's closed under the multiplication. And then argue whether or not we can say that W is isomorphic to R. Okay, does anyone have thoughts about this discussion? So if you just plug in these numbers to the expression above, then what is this product? Yes, I believe this is minus 14 and 5. So let's just write this out. So we have 2 times minus 1. This is A and C. And then we subtract 3 times 4. And the second component, the y component, we have A times D. This is 2 times 4 plus minus 1 times 3. And this is 12 minus 2, which is minus 14. And the lower one, we have indeed 5. Okay, so now if we write this out in terms of the basis, then this would be minus 14 plus 5i. Okay, so what happens if we try this multiplication in terms of the vectors? So if we have 2 plus 3i minus 1 plus 4i, then if these were all real numbers, then we would just multiply them. Like we would multiply each of these summands with each other. So we would have the cross terms and the other terms. So we have 2 times minus 1 plus 2 times 4. But now there's an I, so let's just treat the I to be part of the number 4. Plus 3i times minus 1 plus 3i times 4i. And so now when we evaluate this, this is minus 2 plus 8i plus minus 3i plus 12 times I squared. Now, what is I squared? If we just try to deduce this from this formula given above, well, I is equal to just the vector 0, 1, right? That's just the tuple of the vector I. So if we compute I squared, this is going to be 0, 1 times 0, 1. But by the formula above, this is going to be simply minus 1, 0. And this is going to be minus 1 if we write this back in the basis. Well, this is interesting. I'm not going to say right now why exactly, but let's just use this this computation as an aside, and let me maybe move this down. Let's continue computing this product. So now I can replace this I squared with minus 1. And I'm also going to just pretend that the I behaves, that the multiplication with I behaves distributively over the sum. So that I can write minus 2 plus 8 minus 3 I plus 12 times minus 1. And then you see, well, if I combine now everything with an I and everything without an I get minus 14 plus 5i. Any questions about that? Andrew's question seems to be It is right, but I'm not sure why you would ask that right at this point. Yeah, it is true. So this means we can treat, so this calculation is more like an example to show you how to treat complex numbers if you don't write them in this nasty two-tuple form, but if you just write them as like the way that we usually write complex numbers in math. Okay, let's keep going. Any thoughts about 2? Yes, Adrian.
I think you can just like choose 2 points in W, so like some random A and B, and basically we can just write A plus I times 0 multiplied by B plus I times 0.
Yes.
And then if you just do the calculations, you would just get A times B after the formula plus 0I. And that's just again in the span of 1.
Yes, correct. So these were in W, and this is also in W. So yes, it's just conserved under it is preserved under the multiplication. And then lastly, any reason why this is isomorphic to the real numbers? Well, this is something that we've had before. Yes, exactly. Jency wrote it in the chat. Because both are vector spaces of dimension 1. Okay, so this was the first discussion with complex numbers. Let's look at one more definition and discussion before we'll end the lecture. So the first definition is, okay, now we've established that it's much easier to write a complex number in terms of this basis and not in terms of tuples, because then multiplication is just the multiplication that we already know if we keep in mind that I squares to -1. So we give these now names, and this is motivated by the third discussion point here, that a number with no I in it is isomorphic to a real number. So this means that we call the first summand without the I the real part, and we just write that for a complex number, re of this number is the real part, and the imaginary part is the coefficient of the I, so the second entry in this tuple notation. Okay, so let's let's only focus on the second discussion point right now. No, actually, the first two are interesting. So without any time to think about this, do you have any ideas of what the roots of x squared plus 1 now are? Adrian, your hand is still up. Do you want to say something?
I was from earlier, but I think it should just be plus minus I.
Yes, yes. So P has roots plus minus I, because P of I is equal to I squared plus 1, and this is -1 plus 1 as we saw from before, and this is 0. And same with minus I, this is minus I squared plus 1. Well, if you have minus times minus, this is plus, and then I squared is still -1. So this is still -1 plus 1, which is also 0. So first of all, notice we've achieved our goal already. We've already found roots of this polynomial. The second step is, well, the second comment here in this discussion, the second point. Can you argue which complex number? So I pretty didn't say this. Z is supposed to be another complex number. So Z is equal to a plus ib. Which complex number multiplied with I is equal to 1? Yes, correct. 3 students wrote this at the exact same time in the chat. It must be right then. So if we observe, well, let's call z, let's give the real and imaginary parts of z the names a and b, and then I times a plus ib is ia plus I squared b. We will just write this as minus b plus ia. And if this is supposed to be equal to 1, this means the real part has to be 1. And so this is equal 1 if and only if the real part of minus b plus ia is 1 and the imaginary part of minus b plus ia is 0. So this means that b has to be minus 1. And this means that I times minus I is 1. And we can also conclude that the inverse of I is equal to minus I. Okay, we're over time now. I just wanted to finish the idea of this, the train of thought that this I is now a new number. It's not real. It's complex. It's sometimes called the imaginary unit. I don't know if I say this somewhere. And this exactly solves the problems of finding a square root of -1, and it solves the problems of finding eigenvalues to certain transformations like the rotation. So that's what Andrew was referring to, that if we still keep the idea that eigenvalues are the zeros of the characteristic polynomial, then we have now found numbers that satisfy this. The only question is how do we interpret this and how do we work with this? But that's it for today. I'm going to stop here and I'm just going to stick around for questions. So if you have no questions, you're free to go. No problem. You're welcome. And I'll see you next week. Yes, Andrew, you have a question.
Oh, hey, Professor. So I was just wondering if a transformation has a complex eigenvalue, does that mean it doesn't have like an eigenvector since it's not in the vector space, like the vector that is associated with the complex eigenvalue that's not in them?
Right. That's a good question because I guess solving the issue that there's no eigenvalue is only a part of the answer that has to be addressed. And you were referring to the second part. What about the eigenvector? Is that still like real eigenvector? And the reason and the answer is we need to upgrade our vector spaces from real vector spaces to complex vector spaces. So this means what we're going to do next week is we're going to instead of allowing only, so the scalar multiplication was a times v. This looked like, I mean, if you have a tuple, then let me just say this, the scalar product. This means that a has to be a real number and v is a vector in v. So this is the old way, but now we actually want to consider scalar multiplication by complex numbers. So you want to have z times v, where z is in the complex numbers. So we're actually going to have a plus ib v. So we have to work with vector spaces and vectors that allow to be multiplied by complex numbers.
Oh, okay. That's so cool. Thank you.
No problem. Okay, Aditya.
Yeah, could you go back to the previous 9.1 PDF?
Oh, yes, absolutely.
It's on the discussion that we started with at the beginning of class. The true or false.
Yes. Is it, where is it? This was, yeah, okay, I know. Yeah.
Yeah, so I'm still confused about the first one, because you said that we can take out the lambda I and then we get that determinant t is not equal to 0. But
Yeah.
wait, aren't we assuming that 0 is not an eigenvalue? So isn't that not possible?
Oh, okay. So do we have somewhere to write? So the statement that I was referring to here is that lambda is an eigenvalue. If and only if the determinant of t minus lambda idv is equal to 0. And now if I have the opposite, if I have like the this also means that if lambda is not an eigenvalue, is equivalent with determinant t minus lambda idv is non-zero. These are just two statements which are equivalent. So now when I now set lambda to be 0, then it doesn't matter whether lambda is its eigenvalue or not. I can make an assertion. I can make a statement that is true for lambda equals to 0. I just specialize this statement above for lambda equals to 0, and then I get that 0 is not an eigenvalue. Is equivalent with the determinant of t minus 0 times identity is non-zero. But now if I multiply the identity transformation or even the identity matrix In with 0, well, then t of a vector is equal to t minus 0 times another transformation, in this case id of v. So this means I can just ignore that this is just 0. So this means that this is equal to the determinant of t. And this means that the determinant of t is non-zero if and only if 0 is not an eigenvalue.
Oh, okay. Yeah, that makes sense. Thank you.
Okay, no problem. Let me remove this page again. Any other questions? Siddharth.
Hey, Professor. So I had a question about the assignment response that we got, like TA comment on our assignment, one of the assignment questions.
Okay.
I can put it in chat. Like I just don't understand what the TA was getting at.
Is it only, the screenshot, okay.
Yeah.
If it takes longer, then I actually have to go somewhere. I have a seminar now. But yeah, could you send me this via email, and then I'll just look at this later.
Okay, for sure.
And I'll just respond with a comment.
Yeah, thank you very much.
Okay, no problem. Any other questions?
Bye-bye, thank you.
Okay, bye.